Okay, good. All right, the Java topic for the day, and I think it's probably the last Java topic for a while, is something called casting. And I can show you on the computer, but it'll take more time than we'll spend on the board here. Imagine you could have, a variable I, an int, and say that's equal to 3, and you have a double x, which is equal to, say, 5.0. And I don't think Java requires you to put the 0.0, but I have kind of a habit of whenever I initialize a double to make it look like kind of a decimal, something that might have a fractional part. In fact, why don't we make this 5.9? So in fact, it does have a fractional part. And if you try assigning the x value to I, you'll get an error. And it'll be a message that warns you that you're losing the fractional part. So casting is a way of saying, yeah, I really mean to lose that fractional part. So if you put this sort of expression in front of the x to say, I'm turning the x into an int, the Java says, okay, you know what you're doing, I'll let you do that. And the consequence is that it doesn't round. You'll end up with 5 in I. So it merely lops off the fractional part. There are math functions built into Java, I believe, round, I'll have to look this up off the top of my head, I think it's round, or possibly ceiling. Does anybody use, is seals? Okay. And if you really want to lop off the fractional value, use for. So that's, the Java topic actually today is fairly short and sweet. Although casting kind of is not limited to just expressions like this. You can have objects that you cast one type of object, like for example, you know, an animal A, and you want to assign I think you can just assign a line to this, for example, here. Once, I'll have to look this up. Sorry. Let's say you just have a line object. And I'll have to double check, but you may have to cast this into an animal in order to set it to an animal pointer. It's called down casting. In C is actually, yes, sorry.
Can you only do that when the thing you're casting is
That's just going to get that,
subclass?
right. Java is fairly restrictive that you can't just take, for example, a string and make it into an animal. C and C++ will actually allow you to do stuff like that. And you'd better know what you're doing when you do it. And if you do it sort of indiscriminately, you generally will just kind of usually create some bug. Does anybody have any questions about casting? The reason I bring this up is that at some point in our data structure section, searching and sorting stuff, we'll end up having to cast things. So I just wanted everybody to be familiar with the practice. No questions? Okay. All right, yesterday, there was, I brought up this expression of saying, you know, don't put this inside O, but instead write ON squared. So, I'd like to kind of justify why you can do that. And so this thing here, this expression, is really our P of n. And if we consult our formal definition, we say P of n is O some G of n which we're going to say potentially is n squared. G of n. If there exists some C, some constant C greater than 0 for some n, for some, let me say for some n, and 0, such that for n, all n greater than or equal to this n0, it is true that okay, so in this particular case, our P of n is this guy here, 2n squared plus 1. And G of n is n squared. So the question is there a C? Can we find a C where, let's say, can we find a C and an n0 where for all n greater than n0, this inequality holds? So we need to find C and n where this becomes true. Okay, so we're going to play kind of one of those clever substitution tricks that mathematicians like to do. So let's say for n greater than or equal to 1, we probably would agree that 2n squared plus n squared is greater than or equal to our original P. Because at 1, this is 3, and at 1, this is also 3, so the equals kind of comes into play here. And above 1, for example, 2, this is 5. This is 2, let's see, no, 2, this is 4 times 2 is 8, plus 1, this is 9. This is 8 plus another 4, this is 12, so 12 is greater than 9. And you can kind of convince yourself that the inequality is greater the bigger n gets. So let's say our n0, 1. But what would our C be? Can we find a C? And, excuse me? Right. So this actually reduces to 3n squared. So in fact, as long as this is 3, or it can be greater than 3, that inequality will hold. In fact, it probably, let's see here, you probably, no, it can't be less than 3 because at n equals 1, this side would be less than that. So we in fact did find a C, 3, and n0 equals 1. So, which makes this inequality true, and therefore we can say that Pn is O(n) squared. So is everybody, Ruth?
Is it somewhat standard to look for C's that are integers? Because you said it can't be less than 3, but it can if just n0 changes.
Excuse me, if it's, oh, you're right, if it's, wait a second, does it need to be, no, if it's less than 3 and n equals 1?
Right, n equals 1 doesn't work anymore, but you said as long
Oh, I
as
see,
n
and
is
if you
less
pick,
than
if you
some.
pick a different n, if you pick a,
Right.
a higher n or a lower n, then you can play with the coefficient. It doesn't necessarily have to be an integer,
Okay.
but typically, n is an integer and the number of operations is an integer, so we kind of stick with integers. But,
Oh, and I guess the reality is it doesn't matter what C is, as long as you
Right.
found one.
you need to find one, just one.
So as long as you
Right.
find one, it doesn't.
Exactly.
Right, okay.
Right, great. So does everybody follow sort of this logic that in order to be able to say this is true, and I'm going to do a couple more examples. In fact, I'm going to show you an example where you can't say something like that. You eventually conclude that your assertion that is not true to begin with, but that's sort of a chain of logic. So it takes a little practice, but I think it's kind of a, in particular, this little trick here is kind of clever. Hey. All right, so now we'll take another look. We'll take a look at another example and kind of analyze or determine if we can say certain things about it. The P of n is simpler this time. It's simply n. And eventually you'll get to the point you'll say, well, clearly that's O(n). But I want to sort of play some games with this. Okay. Can you say that P of n is O(n) squared? Would that be accurate to say, or would it be true to say? Can you say that at all? Yes. And here's the reason. Let's say, in order for this to be true, let's go to our inequality here. So we need to find some n0 above which this inequality is true, and we need to find some constant here that also, some constant and this n0 which makes this inequality true. Now let's take a look at our Pn, which is this 45-degree line, and then our proposed G, which is a parabola, which starts out at 0, and below 1, actually it's below the 45-degree line, but then eventually crosses it at exactly 1, 1, 1, and the parabola then stays above our P of n. So conceptually we say, yeah, that looks like it might work, but let's sort of do this a little more step-by-step wise and sort of using some of the logic from our math definition. So let's propose that n0 is 1, and we need to find just some c that will make this inequality true. Right? So 0 and Cn squared. And we don't really even have to do sort of the substitution trick. You can see that if you make this 1 or greater than 1, that this inequality will hold for n greater than or equal to 1. So yes, we have found an n0 and a c that makes this inequality true. So yes, you can say that is, this statement in fact is true, but it's not really the best statement you can make about P of n. One, probably it would be more accurate to say it is little o n squared. That, sure, it's bounded by n squared, but it's very loosely bounded. And that's what the little o means. Okay. So what would be kind of a better way to express the nature of Pn rather than n squared? Ruth? N, right. In fact, it's already up here. Okay, so let's in fact, once again, go through this for n. So here we have our graph. We have P of n equals n. And we write our inequality. And in this particular case, this is n less than or equal to some constant n. So we need to find an n0, and we need to find a constant where this becomes true. And it turns out that n can be 0, and the constant can be 1 or greater than 1. If you make it less than 1, let's say 0.9, and obviously, not obviously, if you play around with that, then it becomes clear it's not true. But as long as this coefficient is 1 or greater, this inequality holds. So once again, we found an n0 and a c, so we can definitely say that Pn is On. Proof.
Wouldn't it be kind of standard then that anytime you have a variable with no constants attached to it, that the big O is exactly what P of n is?
Yeah, and I'm just using our math definition here to sort of beat the thing into a pulp. Okay. But you'll eventually sort of take the shortcut of saying, oh yeah, if your expression is n cubed plus, 3n plus, log of n.
Well, I wasn't even going that far. I was just saying, like, P of n is n cubed. Then
Oh, sure, right. And then, yeah, but in this particular case,
too, but,
right, you replace, in fact, each one of the less powerful functions with, well, if you're going to really beat it to the pulp, the shortcut you'll take is you'll say, the n cubed is the most powerful term in this expression, and just forget everything else. Because as n gets really large, this just becomes the dominant term. Okay. And incidentally, saying Pn is On rather accurately expresses the nature of Pn. So that's as good as you can get. All right. So now let's play some more games with this. It's too bad Chris is not here because he really appreciate this, I think. Okay, can you say Pn is O log n? I see Iowa shaking her head no. Okay, she's right. You can't say that. Sort of by inspection, you would say, well, of course it's not log n. There's no reason you'd call that log n. But I want to use our math definition once again, sort of to beat the question into a pulp. So we start with our inequality. Okay, and we need to find an n0, and we need to find a c that make this inequality true. So, okay, first let's graph this negative territory here. At 1, the log is, before 1, the log is below the x-axis, and then it goes off and does something like this monotonically. In the meantime, our n goes off like this. So the good old plain log function and our linear 45-degree line, they don't even cross. So you'd say it's absurd to say that log n is an upper bound on n. But, very curious thing happens. If you were to multiply this, okay, so log n is 0 at 1, and n is 1 at 1. At 2, I'm going to use this a little bit. Okay, at 2, log n is 1, and n is 2. Now, if we were to multiply our log function by 2, so we have 2 log n, then our log function would now pass through 2 at 2, because log of 2 is 1 times 2, so we go through there. So our log function takes off like this. And so you're saying, aha, okay, maybe at n0 equals 2, if our c is 2, then we do in fact have an upper bound over n. And who thinks that's going to, no, who just knows? Okay? Eventually, the log function, it's sort of exaggerated there, it keeps going up and up, but eventually it crosses back like that. So, so even though we have found a place where the log of n times some constant is in fact above n, it doesn't stay that way for a while. And the condition is that for all n greater than or equal to n0, so this condition doesn't hold. So we cannot find a c, no matter how big, that makes this inequality true. So you cannot say that Pn is O log of n. So this is kind of proving it by, I'm not sure which one of these, well, contradiction, or, well, let's say, this is, you prove that this is not true by saying that there's no way you can find a C, no matter how big C is, because eventually it'll arc back and cross the line and go under it, so it no longer bounds it. So you can't say this for these reasons. And I think I probably muddled it enough for mathematicians to not really be happy with the way I worded it, but that's the general idea. That we can't make our inequality true, therefore you cannot say that is true. Okay. Your homework has a couple of problems that, in homework 3, has a couple of problems where you need to find a couple of exercises in finding curves that bound sort of data sets that you come up with, much like we did for the binary search. So, for example, imagine if you come up with a table, 7, 8, and P of n is 6, 8, 10. This is entirely fictitious. I mean, but you may find you come up with a table like this by analyzing an algorithm. Okay, so you have a certain, for each n, you have a certain number of primitive operations. and you discover that for n greater than or equal to 3, you look at a lot of these things, that p of n is n squared plus 1, with the sole exception of 4. 4 doesn't quite evaluate to that. It should be 17, but for some reason it's 18. It could be sort of like the array list thing I told you about yesterday, that for some reason when you hit n equals 4, there's some extra operation that happens that doesn't happen, you know, for the rest of your numbers here. Maybe it happens again at 9 or something like that. So in other words, you've got a function that's kind of, you know, that's close to your data, but, you know, there are some exceptions. So we're going to, but you want to discuss the exceptions. That's the whole point of this, is to discuss the exceptions. And so n squared plus 1 at 0, n equals 0, is 1. At 1 is 3. And notice that your p of n is 6. You know, so that's, in fact, I'm going to scale this somewhat. So let's make that 10, 20, because we're going to go all the way to 65 here. 30, 40, 50, 60. Okay, so in fact, let's graph our data first. Okay, so at 1, n equals 1, we have 6. N equals 2, we have 8. At n equals 3, we have 10. At n equals 4, we have 18. N equals 5, we have 26. Let's do 6. Well, we'll do them all. 6, 7, 8. 6 is 37. 7 is 50. And then 8 is 65. So what you end up with actually here is this very nice parabola, except 4, this is 4. 4 is just a little higher, just a little above. The rest of the points actually fall precisely on this parabola. N squared plus 1. So the question is, you want to characterize this including its exception of 4. And we don't want to characterize it as, you know, n squared plus 1. We want to actually say we want to characterize, in fact, the whole thing is O(n) squared. So we need to find some c so that our p of n's, all our p of n's, satisfy that inequality. And we're not going to just put this algebraic expression in here because p of n is kind of discontinuous here. In fact, it's one of these, it's like the array list thing where it's kind of this weird function that has a little jump right at 4. So how do we go about finding a c of n to demonstrate that, in fact, this thing is still O(n) squared? Is let's look at 4. So if n is 4, this is 16. C, if we want this greater than or equal to 17. I'm sorry, you're right. Never mind. Great. So, you know, what does C need to be? Simply C has to be, and this is a case where it's not an integer, 18 over 16 or 9/8. So we're able to find the C, and in fact, this is true, in fact, for the entire range starting from 0. And since we're able to find the C, and n, where,
Wait, that's not true, is
excuse me?
it? At 0, 1 is greater than 0.
At n equals 0, our p is 1.
Right, and your O is your 9/8 n squared is 0.
Oh, you're right, it's not, okay. That's, thanks. So in fact, we need to find an n 0. And you're right, it's a parabola that begins at 0. And 9/8, at n equals 1, it's y equals 9/8. So, I'm not sure, I need to kind of zoom in on here, where exactly that crosses.
Shift it over 1, so n squared plus 1 means a shift to the left of the original parabola. So,
Is it n squared plus 1? I thought it's
sorry,
n?
shift the right, shift up.
Oh, right, right. And so this other parabola, so our 9/8 n squared is a parabola that starts here. And it crosses here somewhere.
Yeah, just make it.
And that's our, and actually, it's not gonna be so different. It's actually, it will go through this point, and it will cross at some,
If n0 is 1, that's like definitely going to be.
it'll be, at n equals 1, it'll definitely be above,
Yeah.
let's say,
No, it's.
No, wait.
You set them equal to each other, so you have 1/8 n squared.
Oh, yeah.
So then you have n
Duh.
squared equals 8, so 2 root 2 is n 0.
let's go back, yeah, to 8th grade algebra. So n squared plus 1, so this becomes 1/8 n squared equals 1/8. So this 2 times the square, duh. 2 times the square root of 2, which is about 3 or so. So it'll cross, actually this parabola then will cross just short of 3. So the n, actually, now that we've kind of basically done this math here, your n0 you can say is 3. At 3, this inequality is true when c is 9/8. So since we were able to find a coefficient and an n0, you can say that p of n represented by this table of values is in fact O n squared. Ruth?
Is there a reason to get that specific and not just sort of, like, if you made C2, it still works? and
Yeah,
it's
no,
probably easier.
right, exactly. So you,
Okay.
and it's only if somebody says, well, if it's gonna be 2, well, that's, it's kind of, the performance is too slow. Well, you say, well, it's actually not 2. It could
Oh,
be
so you
better.
actually do get down
Well,
to that?
yeah, if you really need to.
Okay.
Yeah, but the point is, yes, if you say, well, 2 works for some value, then,
Because it'll still be,
Okay.
big O times
yeah.
squared.
Thanks, Samson, for, of course, it's all recorded on video, the ability to do algebra. Okay. So now, I'd like to kind of switch topics and show you a couple of examples of algorithm improvements. And consider, for example, some function of x. You need to calculate the value of some function of x. And this function of x is 1 plus x squared plus x cubed plus x to the nth. So technically this is a function of both x and n. It's sort of like, well, there's a power function, which I'll talk about shortly also, that takes 2 values. But this is just, you're trying to calculate this number. So I'll toss this out to you guys. How many additions n minus 1. This is a little harder. The number of multiplications. Here it's 0, here it's 0, it's 1, it's 2. So it's exponent minus 1. I don't know what to do. So if we add up all the multiplications, we end up with the expression n times n minus 1 over 2. I just happen to know that. This is in fact, another form of Gauss's formula. When the sum is I equals, the sum of I, from I equals 1 to n minus 1. So if we put together a P of n, where we consider the additions and multiplications, it's n minus 1 for the additions plus n squared minus n over 2. If we do a little algebra, hopefully I can do it properly. Over 2, 2n over 2, this n cancels. So we have n squared plus n over 2. So rather than going through our, math definition and kind of beating to a pulp, how would you characterize P of n? As O of, I'm sorry?
N squared?
N squared. So as n grows, this calculation grows as n squared. Unless there's a performance of it, the amount of time on a given computer, on the same computer in the same conditions. So the question is, can we produce this number that we're looking for with a better algorithm, an algorithm that has an O that's better than n squared? And it turns out that you in fact can. It's kind of a trick, one of these math tricks. People like Gauss sat around, they're kind of like obvious to Gauss or something, but you can change this by refactoring. Take these terms and pull out an x. When you pull out an x, you curiously get and you can keep going. So 1 plus x. And here, out of these guys here, you can pull out an x. 1 plus x. And 1 plus x squared plus n minus 2. And the only problem with this sort of analysis is that you eventually have a lot of lines of such things, and you're not entirely sure when you should end, but you might notice something here, that you've effectively reduced the number of multiplies that you'll have to do. And let me illustrate this with kind of a short version of this. Let's just consider these three terms. So let's reduce this to, so here we'd have to do 1, I'm sorry, here actually, let's add an x cubed. Here we have to do 0, 0, 1, 2. And if we rewrite this as 1 plus x squared, which is 1 plus x we end up doing 2 multiplies here. there, and there. And then we do n additions, 1, 2, 3. So we've reduced the number of multiplies by 1. You might say, well, if you do this with a long enough expression, you begin to discover that the number of multiplies begins to drop fairly substantially compared to doing it sort of the original way. And so let's try to come up with an expression P of n for the number of additions and the number of multiplications. So the number of additions here is n. 1, 2, 3, 4, n equals 3. And the number of multiplies, it turns out, is, in this case, it's 1 and 2. So it's going to be n minus 1 multiplies. So your P of n is 2n minus 1. So I'll throw that out to you guys. How would you characterize the performance of that approach? If P of n is 2n minus 1, it's O n. So by just doing a little algebraic manipulation, in fact, I used to have a business partner who said, he was kind of a mathematician, probably. In fact, I learned a lot about programming from him, but he's also learned a lot about math from him as well. Not that it really shows, but he said, you should do a lot of the work yourself on paper so the computer doesn't have to do it later. And this is an example of doing something clever on paper that eventually changes dramatically what goes on in the computer. So that we've taken the calculation of a particular number and changed the algorithm from O(n) squared to O(n) just by doing a little algebraic manipulation. So the hopeful thing about algorithm development is that if you have an algorithm that's bad, it's oftentimes possible to do something to change its nature quite dramatically. This particular transformation is something called Horner's method. And the reason it's particularly useful is things like in a computer, sine, cosine, and a bunch of like the transcendental functions. They're calculated with infinite series. How many of you in calculus have sort of derived infinite series for, say, for Ruth, for a function that usually it's something like, you know, what is like cosine? 1 minus x plus. You don't remember the coefficients? Okay. So you can take, for example, the.
It's been a while.
Yeah.
Did they actually just mean the f of x you have up there with the signs that you take?
No, there's some
Oh, no,
coefficients. Yeah, there's some coefficients as well.
Maybe 1/2.
Yeah, the coefficients are a
They're
function of
related.
I, so that right, they're related, right? So you can write an expression for them as well. But the so rather than computing, and oftentimes you have to compute a bunch. Well, you don't compute an infinite number of terms, but a large number of terms, so that the calculation of these things is significantly more efficient when they're implemented, and I'm sure they're implemented using this sort of technique.